All right, we're good to go. Go ahead.
Okay, thank you. Thank you very much for this introduction, and thank you for inviting me to speak here. I'm going to talk about a theorem, almost 20 years old theorem by Friedman and Megidor. So the theorem, Friedman-Megidor theorem. This theorem answered the following question. So it was open whether we can control the number of normal measures, get any prescribed number, reasonable number of normal measures on a measurable cardinal just from the consistency of the assumption that a measurable cardinal exists. And Friedman and Megidor showed that it's possible. So I'm going to phrase it a little bit differently than the way they phrased it in their paper. Assume V is L of U. That's not how they phrased it in the paper. Let kappa be the measurable cardinal. And fix any tau cardinal less or equal than kappa double plus. Then in a cardinal preserving forcing extension, kappa remains measurable and carries exactly tau normal measures. So that's the theorem. They didn't state it like that in the paper. They started from an arbitrary GCH model, not V equals L of U. But then the next step was to code the universe with the real, to transform the universe into more or less L of U with R some real, and then to proceed with the forcing from there. So essentially, the main argument is done over L of U. And the really nice and cool thing about the proof of this theorem is how many things, how many techniques its proof uses. So the main idea, as I see it, is that Friedman and Megidor identified the components that assemble normal measures in forcing extensions. And for each one of them, they included a feature in this forcing that's designed to control it and constrain it in order to get this very good control over the number of normal measures. So this really cool thing might also be the thing that makes this forcing construction a bit complicated, because it's not like we have a single uniform simple idea behind the proof. We have a lot of components. We have a generalization of Sachs forcings that plays a certain role in the proof. We have a certain iteration with a certain support, non-stationary support, that plays an important role in the proof. We have coding posets that code the generic information that we force, and they play a very significant role in the proof. And we have the assumption that V is L of U that plays a significant role in the proof. So what I want to do is to try and give an alternative proof that is much simpler. It avoids the assumption that V equals L of U, but it also avoids a lot of the methods that I just said, the generalized Sachs forcings, the coding posets. So we're going to prove the following theorem. So assume that kappa is measurable. In an arbitrary ZFC model. And fix tau. I'm saying here less or equal than kappa plus. tau is the number of normal measures, and to get the number of normal measures being exactly kappa double plus, this was known before the Freeman-Megiddo theorem. It was known just performing the Kunin pairs forcing. So it's not hard to blow the number of normal measures to be the maximal number it could be under GCH. So let's just take care of tau less or equal than kappa plus. Then there is a forcing extension that preserves the cardinals kappa, kappa plus, and the measurability of kappa. Measurability. We just this. Such that, so first, every normal measure U in V on kappa lifts in tau ways. So we will have lifts of U star eta for every eta less than tau. All of them normal measures on kappa in VG. Let me add here also something that we didn't have in the original Friedman-Megiddo forcing. All of them have the same ultra power model. So the same ultra power model, not the same ultra power embedding. Their embeddings differ. And every normal measure W in VG on kappa has this form, has the form U star eta for some U in V, normal measure in kappa, and eta below this tau. So in an arbitrary ZFC model, that has a measurable, we can perform this forcing, which kind of multiplies each normal measures into tau many normal measures. If we force over L of U, we get the same result like the Freeman-Megiddo theorem, because we start from a model that carries a single normal measure on kappa, but we don't need to force over this kind of model. I mean, every ZFC model, if we have a measurable cardinal kappa that carries a single normal measure in the genetic extension, this normal measure will multiply and we'll have tau many normal measures on it. And so there are several things. One of the things that are different, one of the main things that is different from the original Freeman-Megiddo forcing is having a single normal ultra power. All those lifts of U have the same ultra power, which wasn't the case in the extension with the Freeman-Megiddo forcing. Another thing, which is, I think, notable, is that the forcing we're going to use is very simple. So maybe even let's just say what the forcing is. We're going to change it a little bit. But mainly the forcing is going to be the following thing. So let's just first, let's assume that tau is below kappa. It's going to be a bit simpler to phrase the forcing this way. And our forcing, let's denote it by p tau. It's just going to be functions from the set of inaccessibles. So maybe let I be the set of inaccessibles below kappa. So we're looking at functions from I to tau, which are partial. And the domain of the functions is nowhere stationary. I'll define this in a second. This idea of using nowhere stationary supports or domains for the function, this idea already appeared in the proof of the Friedman-Megiddo theorem. It was one of the main ingredients in their proof. So basically, that's going to be the forcing. Let me just say what happens in the case where tau is either kappa or kappa plus. So if tau is kappa, we're just looking at functions such that each f in p tau also satisfies that for every alpha below, for the alpha in I, f of alpha is below alpha. So the functions are going to be functions from I to kappa, such that for every alpha, f of alpha is below alpha. And if tau is kappa plus, we have a similar restriction, f of alpha is below alpha plus. Something like this was done also in the original Friedman-Megiddo proof. The main case, I think, is that tau is below kappa, and for tau above kappa, I used functions that represent tau via every normal measures. So tau equals kappa is represented by the identity function, and kappa plus is represented via every normal measures via the successor function. So for tau equals kappa plus, we're looking at functions that map each alpha in I to something below alpha plus. And how does a generic for this forcing looks like? Let's just concentrate for simplicity on the case where tau is below kappa. And let's assume let G be a generic for p tau over V. Oh, I didn't define what is nowhere stationary. So let me just do that. Let's do it here. So a set of ordinals, basically, A is called, let me say it for a set of inaccessibles, because I'm not sure the same terminology will be used for an arbitrary set of ordinals. Oops, sorry. Is called nowhere stationary if for every inaccessible lambda, A intersection lambda is non-stationary lambda. So it might be better to call it non-stationary inaccessibles, but for sets that consists of inaccessible cardinals, it's even equivalent to saying nowhere stationary at any regular cardinal of uncountable profinality. Okay.
Eyal, can I ask a stupid question?
Yeah, sure.
Okay, tau here can be finite, right?
Sorry?
Tau can be finite.
Yeah, tau can be true.
Oh, I see. Tau can be two, and then cases just functions into zero. Okay.
Yeah. So yeah, I think even the case tau equals 2 is the main case. I mean, we're not going to divide it into those cases, but the main idea is to present this forcing as kind of point forcing, just within nowhere stationary support. for the Cohen functions instead of bounded support.
Okay, so tau being 2 gives you a single normal measure. I see. Okay.
No, tau equals 2 give us two normal measures in the generic extension. Yeah. So
okay, so the most you can get is you can have 2 normal. So the one that you had originally extending to 2.
yeah, exactly.
Okay, thanks.
And let's see the main idea behind this splitting of normal measures. So let's look at the generic extension G generic over V. And we can look at the union of G. It's going to be naturally function from I, the set of inaccessibles, to kappa. But let's concentrate on the case where tau is below kappa. It's going to be directly to tau. So just for simplicity, let's assume that tau is below kappa in this discussion. And we can define for every eta below tau a set S eta of all the alphas in I, such that this generic function maps alpha into eta. So what this forcing does, it chooses for every alpha in I, it chooses an ordinal below tau, right? This is the union of G. And S eta is the collection of alphas in which eta was chosen. This is equal. So we will see each S eta is going to be stationary. This forcing, at least in the case where tau is below kappa, this forcing just splits I into tau many stationary sets. And what's going to happen, we will prove that given a normal measure U in V on kappa, U together with with one of those S eta generates a normal measure. U star eta on kappa in VG. And we will also see that every normal measure is generated this way for some U and for eta below the tau that we fixed. So what we did is just to split the measure. If we're looking at I, the set of inaccessibles as a set of measure 1, we split it evenly into tau many stationary sets. We didn't prove it that those sets are stationary, but they will be. And every normal measure splits tau many ways. Just add this stationary set and it will generate a measure in the generic extension. Okay? And so that's the main idea. And the thing that does the majority of the work is the non-stationary support. I should say, by the way, I forgot to mention this, that my original forcing notion that achieves this was much more complicated, not much more, but it was more complicated and it required an additional forcing, and it didn't look like this p tau that we defined here. So this simplified version is due to Omer Ben-Eria. He offered a lot of nice simplifications to my original argument, and this is a much better version than the one I had before. So Omer deserves a lot of credit here. Okay, so so the main tool, the thing that does the majority of the work here is the non-stationary support. So let's talk a bit in more generality about products of forcings with non-stationary support. So non-stationary support. Products are the forcing that we've just defined. This p tau is an example for such a product. So let's keep denoting by I the set of inaccessibles. It doesn't have to be this way in this discussion, but let's just assume that I is the set of inaccessibles. Kappa, we don't need to assume that kappa is measurable as before for this discussion. Kappa could be any Mallow cardinal. And let's, for every alpha in I, let Q alpha be a forcing notion. And the non-stationary support product of the Q alphas consists of conditions P, which are functions from I to, okay, to, let's say, to V, but P of alpha belongs to Q alpha. And the support of P which is the set of alphas in the domain, such that P of alpha is not the weakest condition of Q alpha, is nowhere stationary. Ordered by pointwise extending. So P extends Q for every alpha, P alpha extends Q alpha. So we will typically need more assumptions on those Q alphas in order for this forcing to behave nicely. So we will want Q alpha to be alpha closed, and we will want Q alpha to have cardinality or rank below the next member of I, so below, say, the next inaccessible above alpha. And the main thing when we work with non-stationary support products or iteration, the main tool is called the fusion lemma. So it's not due to me or something like that. A lot of people used it, and it also appeared in the original Friedman-Megidor theorem proof. And what the idea here is going to be, the best thing would be that we'll have some kind of distributivity. If we have a lot of dense open sets, we can intersect them, and the intersection is non-empty. And typically non-stationary support products are not distributive. But we can have some kind of something that replaces distributivity, and that's fusion. We can find, given a very long, a list of length kappa, where kappa is the length of the iteration. So given a list of length kappa of dense open subsets of the forcing P, we'll be able to find a single condition that it's not that this single condition enters each one of those dense open sets, but by a bounded modification on these conditions, we can get to those dense open sets. And if we want to get to the alpha dense open set to get into it, then this bounded modification has to be bounded in terms that depend on alpha. The restriction of the condition, more or less up to alpha plus one, needs to be changed in order to enter to the alpha dense open set. So let's be a bit more precise here. So let's assume that P is the bar. And also assume for all alpha in I, first that Q alpha is alpha closed, and the size of Q alpha or the rank of Q alpha, let's go with rank, is below the next member of I. Then, given a condition, P in P, and the sequence D alpha, alpha less than kappa, of dense open subsets of P, there exists an extension. So there are Q an extension of P, a club C in kappa, such that for every alpha in C, the set of conditions are in the forcing P up to alpha plus 1. I didn't say what it is, so I'll say in a second, for which are joined with the same Q that this Fusion lemma produces, at least its part above alpha plus 1, enters E alpha. And this set is going to be a dense subset of P up to alpha plus 1. So what do we have here? First of all, I should say that products forcing naturally, we can naturally divide them. So P up to alpha plus 1, probably I'll mix those notations. We can just look at it, the non-stationary support product for betas, let's say up to alpha of the Q alphas, but then add the forcing at coordinate Q beta, but then add the forcing Q alpha itself. We want to look at the first alpha plus 1 many forcings. And naturally, given a condition P in P, we can split it into P restriction to alpha plus 1, which will be an element in this poset, and then P above alpha plus 1, so restricted to I above alpha plus 1. That's going to be a typical element in the product of the Q betas, just for beta above alpha, the non-stationary support product. So like a lot of iterations and products, we can split the forcings. That's just an explanation for those notations, for this notation, and an explanation for this lemma. So we have kappa many. I see that I also mixed the names of the dense open sets. So D alpha are the dense open sets. We have kappa many of them. We get a single condition Q such that on club many coordinates for every alpha in C, more or less this Q enters D alpha, but not as it is. We need to modify it a bit. So above alpha, we pick this Q as it is, but below alpha, we have densely many modifications. So as long as we're below the initial segment of Q up to alpha, including alpha, we can extend in a dense way and get with the same Q into the alpha. So this Q enters at least its final segments, club many final segments enters those dense open sets with modifications, bounded modifications. Okay, so that's one of the main tools that is always used when we consider non-stationary support products or iterations. By the way, if there are any questions about that, I know that it's a bit technical, go ahead. So this lemma is going to play a very significant role in our proof. And just back to our forcing, Again, I'm assuming for simplicity that this tau is below kappa. Similar thing can be done for tau equals kappa or kappa plus. If each Q alpha is the same poset, like the weakest condition of Q alpha, and all the ordinals below tau. So like an atomic forcing. So each if Q alpha is like this, where the ordinals below tau are antichains. What is this Q alpha? This Q alpha is just a poset that picks an ordinal below tau. It's a very trivial forcing notion, but the non-stationary support product of those Q alphas is not trivial. So the product alpha in I, non-stationary support product of the Q alphas, is equivalent. Basically, it's the same to our p tau. Just look at functions that for every the domain or the support is nowhere stationary, and for every alpha in the domain, f of alpha is below tau. And since we're able to present our forcing as a non-stationary support product, whose ingredients Q alpha satisfy the assumptions of the fusion lemma, which are just being closed and having a low cardinality. The cardinality of Q alpha is below the next inaccessible above alpha, which will happen if tau is below kappa. It will happen for most of the alphas, almost all of the alphas. So since our poset satisfies the assumptions of the fusion lemma, we can apply the fusion lemma to it. And fusion is going to be the thing that plays an essential role. So let's see how. Oh, I wanted to say something before that. So maybe let's just see an example for an application of the fusion lemma. An application not for our specific forcing, just an arbitrary forcing non-stationary support product where the Q alpha satisfy the assumption of the fusion lemma. So just a simple example for an application of the fusion lemma. So assume that P non-stationary support product of posets Q alpha is as in the fusion lemma. And let's G be generic. Over V. And F in VG be a function from kappa to the ordinals. So a typical application of the fusion lemma is to find the ground model function that kind of dominates F in a way. So what we will see is that we can apply the fusion lemma. So how do we apply it? We fix a list of dense open sets, right? So where for every alpha below kappa, D of alpha is going to be the set of conditions Q, which decide the value, that's supposed to be Q, which decides the value of F of alpha. Okay, that's a dense open subset. By decides, I mean there exists some gamma ordinal such that Q forces F of alpha equals gamma check. So that's going to be a dense open subset of our P. And what does fusion give us? So by fusion, any condition P can be extended to Q such that something happens, but just from this beginning, any condition P can be extended to Q, we can find some Q in G. And what is the thing that happens for this extended Q? It has also a club. So there are Q in G and the club C in V, club subset of kappa, such that for every alpha in C, the set of conditions are in P up to alpha plus 1, such that for some gamma and ordinal are joined with the same Q forces enters, what do we want to say here? R and then Q above alpha plus 1, not below. Enters the alpha dense open set. Entering the alpha is just deciding the value of f of alpha. So forces f of alpha to be this gamma. And this set is dense in P up to alpha plus 1. And how this could be used? So we can define in V a function capital F, whose domain is C, and it maps to each element in C a set, a set of size less than kappa of ordinals. F of alpha, for which alpha in C, is going to be the set of all gammas, ordinals, such that there exists some condition R in P up to alpha plus 1. And such that R together with Q above gamma plus 1 forces the value of f of alpha to be gamma. So f of alpha is just the set of possible values of f of alpha as forced by conditions of this form with the same Q that fusion gives us. Oh, I forgot to say that those are, this is dense below Q up to alpha plus 1. We only care about R's below Q up to alpha plus 1. But anyway, even when we define this F this way, what can we say about the cardinality of F alpha? So it depends on basically on this poset. It's at most the cardinality of this poset, P up to alpha plus 1. And this Q that fusion gives us, it forces that f of alpha belongs to capital F of alpha. This is true for every alpha in C. Since we pick this Q and G, we even get that this ground model function capital F kind of dominates this name F that we started, this F that we started with. So that's a very typical application of fusion. Given a function in the generic extension from kappa to the ordinals, we can find a ground model function that estimates it in a very good way on a club of coordinates, club in V, capital F of, lowercase f of alpha will belong to capital F of alpha, where capital F of alpha is a set of size less than kappa. Its size is the size of this forcing P up to alpha plus 1. So it's even a bound in terms of alpha. Okay, that's a very useful thing because if we initially start from functions from kappa to kappa, for instance, we can get ground model functions from kappa to kappa that dominate them even pointwise, not on a club. So this is something that could be shown using this application of the fusion lemma. This shows that stationary subsets of kappa are preserve their stationarity in the generic extension. This can also be used to show, so I will not show it, but this can also be used to show that kappa plus, that's like the first candidate for a cardinal that has a danger of being collapsed via those non-stationary support products. So this method can be used to show that kappa plus is not collapsed. Kappa is not collapsed for easy reasons, but in order to show that kappa plus is not collapsed after non-stationary support product of length kappa, we can use something. We can use this lemma, a corollary of this lemma, basically the fact that if we have a function from kappa to kappa plus, we can dominate it with a ground model function on a club. If we assume that the initial function was increasing, we can even dominate it everywhere. And this ground model function gives values for the alpha in its domain, values of size below, of size at most kappa. So we can find even a bound on the original function below kappa plus for its image. This is basically the argument why kappa plus is not collapsed. So it was so quick. I just think it's not the main thing that I want to show today. So let's see in our context for our forcing, how fusion gives this how many lifts of normal measures. So back to our forcing. So again, fixed tau less or equal than kappa plus, but we will, as always, take care of the case tau is below kappa. Let G be generic over V, subset of our p tau. And let's just recall p tau is a non-stationary support product of forcings for each alpha and I inaccessible. We choose an ordinal below tau. That's what p tau does. Let U in V be a normal measure on kappa, and eta below this tau. Then we argue that U with S eta generates a normal measure. U star eta in VG. Let's recall S eta is just the set of alphas in I such that the generic function from I to tau mapped alpha into this eta. So all the alphas in which we chose eta, the ordinal below tau that we chose was this eta. So let's see, let's prove this. So let's denote by JU from V to MU. This denotes the autopower embedding. We're going to use the standard methods in order to lift U. We're going to lift JU. So we have V, we have MU. We have G generic for our product below kappa. We're going to look at J of P. Okay, this is just the ordinal J of kappa, so maybe I should. It's just J of kappa. But we're going to look at the forcing poset J of P. And we want to construct a generic age for this poset, generic over M of U. And we want to do this for each eta separately to construct the generic that will provide the lift of JU, whose normal measure, the normal measure derived from it, will be the one generated from U union S of eta. So we're going to provide for each eta below tau a generic edge eta, for the forcing J of P tau. And we're going to see after we derive a normal measure from the lift of Ju that this H of eta induces. This normal measure, we need to prove this, but this normal measure is generated by U and S eta. What is this H of eta, this generic? So that's a typical thing of non-stationary support products and why it's so useful when we want to have nice classifications of measures in forcing extensions. What's going to happen is that the pointwise image of this generic G under J of U almost does all the work, almost provides us H eta entirely. It's going to give us the generic information. If we look at Ju of P tau as a product, it's going to provide the generic information in all coordinates, but the coordinate at kappa. Okay, only kappa itself is not going to be decided by the J pointwise of G. We will have freedom at kappa. And what is the forcing on kappa in J of P tau? If we look at P tau as product, for each alpha in I, we use the same Q alpha, this forcing that chooses an ordinal below tau. This is the forcing that we use at kappa, at coordinate kappa in J of P tau. So basically, we just need a generic at coordinate kappa will just be a choice of eta below tau, right? And that's going to be what the thing that's going to play the essential role here. H eta is just going to be the collection of all conditions Q in J of P tau, such that for some P in G, Q is weaker than J of P. But when we modify it and add at coordinate kappa, we map it to eta not tau. So Q is weaker than this condition. Basically, we take conditions of the form J of P, we modify them such that on kappa, we choose eta to be the generic information, and we close it downwards. Now, we need to worry about this not being, this should be a condition, right? When we add manually that kappa is mapped to eta, we need to make sure that we don't contradict the information in J of P. So that's one place where the non-stationary support is important. We know that the support of P, the domain of P, is non-stationary and inaccessible. So there is a club in kappa disjoint from the support of P. And the image of this club will be disjoint from the support of J of P. And kappa will belong to the image of this club. So that's another typical thing for non-stationary support products and iterations. They don't say anything about what happens on kappa, because kappa will belong to the image of the club distant from the support of P, and thus will be distant from the support of Ju of P. Okay, so when we take conditions P in our poset and we apply Ju on them, it doesn't say anything about what happens at kappa. Kappa is free, and when we modify them by adding that at coordinate kappa, we pick the ordinal eta, we get a legitimate condition in Ju of P. It has a non-stationary support. It's not hard to see that any pair of conditions of this form, Ju of P for P and G, union kappa eta, any pair of conditions of this form are compatible. So in order to show that this H eta, the thing that J pointwise of G generates with the choice that eta is the generic information at kappa, in order to show that this thing is generic, we just need to show that it meets every dense open set of Ju of P, which belongs to mu. So let's argue that this H eta, so we define it for a given eta below the tau that we started with. And let's argue that this H eta is really generic over M of U. And that's going to be an application of our fusion lemma. So maybe let me write again what H eta is. Oops. Sorry. Let me write again what eta is. So we looked at the collection of the conditions Q in J of P, such that for some P in the generic G that we have for P tau over V, for some P in G, Q is weaker than J of P union kappa eta. And we argue that H eta is generic for J of P over M of U. So let's see why. So again, the main thing is to show that it meets all the dense open sets. So let the in M of U the subset of J of P be dense open. Since D belongs to M of U, we can represent it. So let alpha map to D of alpha lowercase d be a function in V such that D is represented using this function. And we can assume that for every alpha, we can assume that D alpha is a subset of P. I see that I started forgetting the upper indices tau. So from now on, P just denotes P tau, where tau is the ordinal that we fix in advance and below less or equal than kappa plus. So we can assume that for each alpha, D alpha is a dense open subset of our forcing P. And then we can apply fusion on the sequence of those D alphas, right? So by fusion, we can find, fusion is, as usual, gives us density. Every condition can be extended to a condition such that things happen. So we can find some P in G and the club C in kappa, such that for every alpha in C, the set of conditions are in our forcing P up to alpha plus 1, such that R together with this P above alpha plus 1 enters the alpha as a subset of P up to alpha plus 1 is dense. Okay, this is what diffusion lemma gives us. And since this happens for a lot of alphas, for alphas in the club C, we know that kappa belongs to J of C. So kappa is one of the coordinates for which the parallel property happens, for not for P, for J of P. So in M of U, the set of conditions are, we look now up at kappa. So we're looking at J of P. Now alpha becomes kappa up to kappa plus 1, for which R together with J of P above kappa plus 1 belongs to D, the D that we started with. This is what the functions D alpha represent. This as a subset of P up to kappa plus 1 is dense, not P, J of P. Okay, this is just because the line above happened for the alpha in a club C, and the C belongs to you. So we have a dense subset of our forcing J of P up to kappa plus 1, but we also have a generic for this forcing, right? We had P in V over M of U we have Ju of P. And we know how it looks. We have Ju of kappa here, we have kappa here. We have an available generic for J of P tau restricted to kappa. Restricted to kappa is just the same as P tau. And at coordinate kappa, what is a generic at coordinate kappa? It's just picking an ordinal below tau. In our case, since we initially started from some eta, which we wanted, which should be this ordinal, we can just pick eta to be the generic here at coordinate kappa. Okay, so we have a generic for the forcing J of P restriction to kappa plus 1. We have a very natural generic. And since we have here a dense subset of this poset, we can find let's call it Q in G, such that Q, when we add at coordinate kappa, we choose eta. This belongs to the dense set. This dense set. Which means that when we take Q, we modify it such that eta is chosen at kappa, and we add J of P, the same P that fusion gave us, above kappa plus 1, this thing enters T, and recall that those Q and P, both of them are in G. Q was chosen in G, and P by fusion. Fusion is a density argument, we chose it in G. So they are compatible, Q and P. We can find a common extension of them inside G. Let's still denote by P, this common extension. So since Q and P are compatible, there is some condition in G that extends both of them. Let's assume just without loss of generality that this condition, not without loss, let's just call it Q or P. So assume without loss of generality that Q is P, otherwise change both of them to a common extension. And what do we get? We get a condition of the form Q union J of Q above kappa plus 1, which is basically just J of Q or P for P in G. And we modify it such that at kappa we add eta, and this condition belongs to D. But also this condition belongs to H eta, right? A typical condition in H eta was this thing. H eta is the downwards flow of those stuff. So we get that this H eta is also generic over mu. Okay, it intersects D. Okay, so maybe let's proceed to the right here. So we have V, we have mu. We fixed our eta. And we have a generic G. We have a generic H eta. G pointwise is pointwise mapped. We have Ju pointwise G is contained in H eta. So by the standard Silver criterion, we can lift Ju. Let U star eta be the normal measure derived from the lift of Ju, which maps G to H eta. Okay, derived by using kappa itself as a C. And we now argue, so it's not hard to see that U star eta is normal, and it's not hard to see that the ultra power of U star eta over Vg is actually going to be this lift of Ju. Those are quite standard things, but less standard thing is that this U eta star is generated by U and the stationary set S eta. So we argue that our ground model measure U when we add a single set in the generic extension, this S eta, this generates U star eta. Okay, so let's prove this. And so given X in U star eta, let's X tilde be a P name for it. So be such that the interpretation via G of this name is X. The fact that X belongs to U star eta and U star eta is derived using kappa as the seed from the lift of JU, this means there is some Q in H eta such that Q forces that kappa belongs to JU of this name. Now, since this Q belongs to H eta, we know how H eta is generated. We can assume that this Q, if this Q is below some condition of the form J of P, union kappa, comma, eta. So let's assume that Q is a condition like this, not only weaker than a condition like this. So assume that Q is J of P. For some P and G. We can assume this because those generate the generic H eta and Q belongs to it. So what do we get? We get, let me write it as it is. So J of P union mapping kappa to eta forces that kappa belongs to J of X. And we can reflect it downwards to say that P, by modifying it, by mapping alpha to eta for a lot of alphas, forces alpha to be in X. And this happens for a lot of alphas, for a set of alpha in U, for a set of alphas in U. Okay, so we get here a set A, a ground model set. This P is a condition in the ground model. It's in G, but it belongs to ground. This entire formula is a formula in the ground model. So we get this set A, which belongs to U. And let's note that A, when we intersect it with this S eta, with the stationary set that we're interested in, is contained in X. This is the main thing that shows that U with S eta generates U star eta. X is the set, arbitrary set in U star eta that we started with. So A intersection with S eta is contained in S. Let's recall S eta is just the alphas below kappa, for which the union of G maps alpha into eta. Why is it contained in X? Because if we pick alpha in this set, first of all, this alpha belongs to A. So P union alpha eta forces that alpha belongs to X. And if we really want alpha to belong to X, we need to make sure that the thing that is forced here is correct. And we can show that this thing that is forced here is correct, assuming that this condition, P union alpha eta belongs to the generic G. Now P belongs to G, we picked this P in G. And we know that alpha belongs to S eta. Alpha belongs to S eta means that alpha is one of the kernels in I that the generic maps to eta. Namely, mapping alpha to eta will be compatible, will be compatible with the generic information. When we take P in G and we add to it alpha, comma eta, we get the condition, this stays in G. And thus whatever it forces is correct. So for alphas in the intersection, A intersection S eta, we get those alphas those alphas belong to X. Okay, and this shows that U star eta is generated by U and this stationary set S eta. Okay, any questions about this proof? So just a quick remark, let's note that all of those U star eta, all of them have the same ultra power model, not the same ultra power embedding, but the same ultra power model, which is mu. When we add to it this H eta, this generic that we chose. Now, this looks like it depends on eta, right? But eta is only the generic value at coordinate kappa. So all of those models, when we modify eta, they are the same. We can compute H eta from H eta prime for eta and eta prime different. How? Just take H eta and modify the generic information that is given at kappa at coordinate eta. It's very useful here and important here that we use the product forcing and not an iteration. If we get an iteration, we lose this property that we have the same ultra power model. We still get the theorem, and we still have those U star eta and they're generated by U and S eta, but this trick with modifying the generic value at kappa now doesn't work because H eta is generated by conditions J of P when we add at coordinate kappa eta, and when we use an iteration, when we change the generic value at eta, we influence the names of the conditions in the poset J of P above kappa plus 1. It is possible that when we take two conditions in this forcing and we modify their value at kappa from 0 to 1, the rest of the conditions turn from being compatible conditions to incompatible conditions. Okay, this can happen for conditions in the generics H eta, not for conditions of the form J of P for P and G. They will stay compatible no matter how we modify the value at kappa. But when we do the downwards closure, we add a lot of conditions. And when we modify each of those conditions by changing 0 to 1, it's not promised that we end up with the set whose conditions are pairwise compatible. So when we do an iteration, this trick doesn't work, but when we do a product, it works because the condition in the interval above kappa, between kappa and J of kappa, it doesn't depend on the generic value at coordinate kappa. You can change the generic value at coordinate kappa from 0 to 1, say, and it doesn't influence the conditions above kappa. They stay incompatible, and when we modify H eta this way, we get a generic H eta prime. We modify the value in kappa from eta to eta prime. Okay, so it is very important here that we use a product and not an iteration. We can still use an iteration, just lose this property that all of the ultra power models are the same. Okay, so we have 20 minutes, so I think it's going to be enough time. We're still not done with our theorem because our theorem gives the full classification, right? We show now that any U lifts in tau many ways. We also need to show that any W normal in VG is such a lift. And the main thing that is used to show those kind of things, can be used to show those kind of things, is the known theorem of Hankins, the gap forcing theorem. Which says that the following thing. Let's assume that we have some delta below kappa, and we have a poset P that factors to the form P0 and then P1, where the size of P0 is below this delta. P0 is non-trivial. And it is forced by P0 that P1 is delta plus 1 strategically closed. So forcing notion that could be split this way, P0 and P1 is called a gap forcing. It has a gap at delta. And let's assume that G is generic over V. And J from VG to some M is definable in VG elementary embedding with critical point kappa. Then J restricted to V. It's going to be from the ground of VGV to the ground of this M. Is definable in V. Oh, I didn't say that M is closed under delta sequences. Also require this. Is definable in V. So this is a very useful theorem that allows to bypass inner model theory when we try to classify measures in forcing extensions. For the Friedman-Megiddo forcing original one, inner model theory was used in several ways, and this helps bypass one of those uses. Because what happens if this J is, say, an ultra power embedding with W in VG? If W in VG is a normal measure, then W intersection V can be shown to belong to V. Why? Because W intersection V is just the subset of collection of subsets of kappa in V, such that kappa belongs to the JW, but it's enough to look at JW restriction to V. And since this JW restriction to V is definable in V, assuming that P satisfies the assumption of the gap forcing theorem, then we get that U intersection V actually belongs to P. Sorry, W intersection V actually belongs to P. And so this theorem kind of shows some kind of amenability of W's normal measures in VG to V. And how can we use it to classify normal measures? And we want to use our forcing P. Unfortunately, this P was defined as a product, not as an iteration. The reason we defined it as a product is just to get this additional property that I was interested in, which is all the measures have the same ultra power. So since P is a product, it doesn't seem like it could be factored to have a gap. It's important that in gap forcings we use an iteration. So it doesn't seem like the conclusions of the gap forcing theorem hold for P. So there are two possible directions here. If we're only interested in the Friedman-Megiddo theorem without having the same ultra power, we can replace this product with an iteration and apply the gap forcing theorem on it. And then with an additional argument that I'll show that any W is a lift U star eta for some mu in V and some eta below lesser equal than kappa plus. Another approach is to add a gap to our forcing. So those two approaches are very similar. I'll go with the second approach because I am interested in having the same ultra power. So we'll leave P as it is as a product, but let's define by R. It will be our P tau, but preceded with the Cohen subset of omega. And let's show that this R actually proves our main theorem. You see that this whiteboard is a bit laggy, so let me maybe change to another whiteboard. Sorry. I think now it should be quicker. So let R, adding coin subset to omega, and then p tau. And let's prove our theorem. Let's show that this R is as desired. So proof of our main theorem. And again, the goal of the initial coin subset of omega, I'm not sure if I said it. The goal is to add a gap to p tau as it is. Doesn't seem like it has a gap, it's a product forcing. We add this coin subset of omega in order to artificially add a gap at omega 1. So let's G be a subset of R, generic over V. And let's write G as lowercase g generic for the coin. And that's not a very nice notation, but I'm already used to it. So G prime, this is generic for coin omega over V. And this is generic for p tau as defined in V G, lowercase g, over Vg. Okay? And we want to prove that in V capital G, we have this classification of normal measures. So first, given U in V and eta below r tau, we know that in Vg, lowercase g, since this coin poset is a small forcing relative to kappa, we know by the Levi-Solovay theorem that U generates a normal measure. Let's call it U prime in V lowercase g. And now in this model V lowercase g, we use our forcing p tau. And we know what happens after we force with the g prime, this generic for p tau. What happens is that U prime union S eta generate a normal measure. Of Vg star g prime. S eta, as usual, all the alphas inaccessible, such that the generic for the forcing p tau, now we call it g prime, maps alpha to eta. Okay, so it's the same stationary set. So let's use star eta be this normal measure. It's defined in V capital G, which is the generic low G, and then G prime. Okay, so we have this list of how many lifts of U. And let's show that any W normal in V capital G is such a measure. So given a normal W in Vg, first we can apply our gap forcing theorem in order to deduce that W intersection V, let's denote it by U, belongs to V. So we have the U that generates W. We need another ingredient in order to understand who is this W, which is the eta. And what's going to be the eta? So denote by eta JW of this function that G prime defines at kappa. Okay, G prime is generic for R forcing P tau in the sense of V lowercase g. JW of it, of the union of G prime, we can apply JW on this and get a function whose domain is the set of inaccessibles up to JW of kappa. Kappa is one of the inaccessibles in the domain, and eta is going to be the generic value that the union of G prime chose. Eta is going to be the generic value that the union of G prime, JW of the union of G prime chose at kappa. So it's much simpler when the initial tau, as we assume while this talk, is below kappa, because then it's clear that this eta is below the tau, initial tau. If we start with tau equals kappa plus, then we know that this thing, if you remember the modification, it's below kappa or below kappa plus. So this eta will be below the tau that we start with, kappa or kappa plus. But let's just assume that tau is below kappa. It's much simpler. Then eta is below this tau. So this is a legitimate eta. And the fact that eta is JW of the union of G at kappa, this means that the set of alphas below, set of alphas in I, for which the union of G prime at alpha was this eta, belongs to W. We know that W is a normal measure. We know that eta is JW of the union of G prime at kappa. So the set of alphas for which the union of G prime at alpha was eta belongs to W. This is just set as eta. So what do we have? We have that U, and U is contained in W, and S eta belongs to W. Now U generates in V lower G. It generates this U prime. And in V lower G and then G prime, U prime together with S eta generates this U star eta. Overall, if we look directly from V to V capital G, we get that U with this S eta, the original U, they generate U star eta, right? U prime is just generated by taking U and close it to be an ultra filter. So U star eta is already generated from U, the ground model measure on kappa, and this S eta is defined using G prime. U is contained in W, S eta belongs to W, so we have U star eta, a normal measure generated by the pair of them, and W, a normal measure that contains the pair of them. So we get that U star eta and W must be the same. Okay, so this is how we get this full classification. And W must be U star eta for some U and V and some eta. Okay, so that proves our theorem. So we insisted on this modification, still using product in order to get that the U star etas have the same ultra power in VG. So we also showed here the consistency of several normal measures, but all of them have the unique normal ultra power. And this can be further developed into classification, not only of lifts of U, also of lifts of U to the n, probably n less than omega, something that can be further developed into get classifications when forcing, say, over L of U, of all sigma complete ultra filters in the generic extension. So I don't think I have enough time to show that, but if you want to get classification of not only of normal measures, but of all sigma complete ultra filters, it's useful to assume that you force over L of U, and the same methods can give you a full classification of all the sigma complete ultra filters. Okay, so I think I'll stop here. Thank you for listening.
Thanks very much. That was a great talk. I understood everything. Thanks for the details. It was perfect.
Thanks.
So I don't even have any questions because I think you made everything so clear. I cannot believe how much simpler the argument is because I know the original argument.
Yeah.
And it was like you drown in the details. I think I've looked at it several times, and every time I would come back to it, I would be like, okay, what is going on? I had to go over everything again because there's so much there. This is
Yeah, I also feel this way.
such an elegant simplification.
Thank you.
Okay, does anyone else have any questions?
Well, I'd like to make the remark that one of the advantages of this, and this is absolutely fabulous work. I mean, I cannot say enough how wonderful this work is. And one of the advantages, which one of the advantages of this is that you can apply it over nine non-fine structural models, as Eyal was saying. So in particular, if you have a super compact and you assume UA, you can now get models in which you have really nice things where you have a certain number of ultra filters of normal measures over different measurable cardinals, and you can use these techniques to generate this without using fine structure. So, I mean, I don't know if I made myself completely clear there, but what I'm trying to say is that if you, probably, based on my understanding anyway, ultimate L is not going to have fine structure to it, or at least the kind of fine structure that we understand. But I believe it's also thought that ultimate L will satisfy UA. So you can, for instance, use this to force and get a model in which you have a super compact and the least measurable has 2 normal measures or 5 or whatever you want. So there's an example of forcing over a non-fine structural inner model. The other comment that I wanted to make about this is that if you try to imagine an alternate timeline, imagine an alternate timeline where we didn't know anything about fine structure, but we knew about non-stationary support iterations and products and all of these results. So theoretically, this is a theorem that in this alternate timeline we could have known around 1970. So what I mean is that in 1970, I think it's based on Cunan's thesis. We knew that in L mu there was only one normal measure. So you don't need fine structure for that. This was known just by the iterated ultra power analysis. So if we had these techniques available, of course we didn't, but if we had these techniques available, then we might have known many, many years ago about whether or not just trying to answer the simple question of a measurable carrying 2 normal measures, what is the consistency strength of that? Now, there's no earthly reason to think that it has consistency strength beyond one measurable. And of course, Friedman-Magidor showed that it does not. But that is a question that was open for, I don't know, between, let's say, about 1970 or 1972, when Cunan and Paris showed that you could force and get 2 to the kappa many normal measures just from any measurable cardinal in any model of ZFC. So between then and Friedman-Magidor, it was maybe, let's say, 35 years or so, roughly speaking, to know that you could just use one normal measure to get 2 normal measures, to force and get 2 normal measures. And this is something that was really, I mean, it was a question that was open. This was something that people did not know about. And, to restrict the number of normal measures, you had to use measurable cardinals of large Mitchell ordering, or Mitchell ordering beyond 1. Mitchell's paper appeared in the 74 JSL, sets constructible from sequences of ultrafilters. And there's where he constructed models, from an O of kappa equals 2, you get an inner model where kappa carries exactly 2 normal measures. Kappa is measurable, but it's an O of kappa equals 2. It's not the least measurable. Maybe about 10 years later, Stuart Baldwin was able to use large cardinal assumptions. So I think it was an O of kappa equals 2. At least this is what Moti said a couple of weeks ago to me. I thought it was beyond an O of kappa equals 2, but it was something beyond the existence of one measurable to get a model in which the least measurable had 2 normal measures, or however many normal measures you want. Baldwin's paper appeared in JSL, I think, about 1985. But again, it's still using beyond one measurable cardinal. And there was no earthly reason to think that you needed to do that. But this wasn't known until Friedman Magidor. And now with Eyal's, brilliant, elegant, beautiful, wonderful work, we don't even need fine structure. So you'll forgive my rambling, but I hope something that I said there made some kind of sense in terms of how important not only Friedman Magidor, but Eyal's work is, and the potential it has for these non-fine structural inner models where we have larger cardinals like supercompacts, extendables, huges, whatever. That we can force over these models and control the number of normal measures using Eyal's techniques, because we assume that we have UA. If we have UA, the Mitchell ordering is linear, and we could just go from there and start getting all these crazy, wonderful, beautiful results. Okay, I think I'm done with my rambling.
Arthur, I actually appreciate the history. I, for instance, never thought about the fact that the question was open for 30 years before Friedman and Magidor solved it.
Yeah, it's crazy because I remember asking Ralph about this, I think in the early 2000s, because no one knew how. So this is before Friedman Magidor, and nobody knew how to get a model with the least measurable having 2 normal measures from just one measurable cardinal. So I remember with this discussion I had with Ralph, that's where he said, that he couldn't see of any way of deriving large cardinal strength. So it took Friedman Magidor to get that you don't need large cardinal strength. You just force over L mu. So it's just, again, it's interesting that this is a question that had been open for, roughly speaking, 35 or more years.
I should say that this main tool non-stationary support was already used in Friedman's Megidor and Megidor's forcing. So they had the idea to control normal measures using this support. Also, I should say again that the original forcing I use is much more complicated and it's not as nice as the one presented here. So it's Omer, I think Omer deserves a lot of credit for this nice presentation of this forcing. Yes, it's important to say this.
And we could also mention that the idea of using non-stationary support iterations is due to Jensen. And of course, if you didn't know this already, Jensen just passed away a few weeks ago. So, but his work and his ideas live on. And this is a descendant, Friedman Magidor, Eyal's work, and Eyal's thesis, Eyal Kaplan, lots of stuff are descendants of non-stationary support iterations and Jensen's brilliant work.
All right, again, thanks very much. I greatly enjoyed the talk, and
thank you.
Let me end the recording first so I don't forget.